Okay, students. All right. I see people are moving along here in Chapter 6 and getting into the universal law of gravitation. And so let's read number 35. It says, what is the acceleration due to gravity on the surface of the moon? Now, you might remember me talking about this, putting two things together. The first is the universal law of gravitation, and the second is Newton's second law. And so to figure out the acceleration, you would take the force and divide it by the mass of that object. And of course, to get the force, you take the mass of the object and the mass of the planet. So let capital M be the mass of the planet and lowercase m be the mass of the object. So putting these two things together, the force would be g little m big M over r squared. And then dividing it by the little m, the acceleration on a planet, any planet for that matter, is a combination of three factors. This universal constant, so I'll call one factor is just nature. The other factor is what is the mass of that planet or moon, and what is the radius of that planet or moon. And you might remember me commenting that if you put in the mass of our Earth and the radius of our Earth, this would come out to be 9.8. So this is asking you to do the same thing, but in this case for a different planet or moon in this case. Because it says, what is the acceleration due to gravity on the surface of the moon? So I'll do the moon first, and so this would be the g, 6.67 times 10 to the negative 11. Maybe I should talk about units also. Then it would be the mass of the moon. Well, I went ahead and printed up a little, this is actually in the front cover of another book. I looked in the front cover of your book and was a little disappointed. They had just the Earth and Jupiter and the Sun, but not all the other ones. So I'm going to focus right here on the moon here for a moment, because it says the mass is 7.36 times 10 to the 22 kilograms, and the radius is 1.74 times 10 to the 6th meters. So there's the numbers. Let me also put in the units. And so the unit for the gravitational constant is Newton meters squared over a kilogram squared. And then this mass would be in kilograms, and this distance would be in meters, and then we'd be squaring it. So what we would end up with is a Newton over a kilogram, which is really good because a Newton is a kilogram meter per second squared. So when you divide it by a kilogram, we're going to be left with meters per second squared, as we should, since we're talking about what is the acceleration due to gravity. So again, our unit analysis works great. We did get the units that we kind of expected. Now let's get a number, 6.67 times 10 to the negative 11. Times 7.36 times 10 to the 22, divided by 1.74 times 10 to the 6th squared. And the acceleration would be about 1.62 meters per second. So really small compared to the Earth. In fact, usually the comment is the acceleration on gravity or your weight is about 1/6 on the moon. So I'm going to take 9.8 and divide it by a 6. Yeah, see, it's almost exactly a 1/6. And so that would be the acceleration, why it would make it so easy to jump. And you can see the videos of astronauts on the moon. Even though they've got so much gear, they don't seem that heavy, kind of bulky, so they can't really walk, but they bounce and boing, 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 and they just kind of bounce that way. And in fact, I think another fun thing the astronauts did was to hit a golf ball, because you can imagine how far it must go without little force of gravity. anyways, that's the moon. I think there's a second part to this, B. It says, what would it be on the surface of Mars? And so we can look up Mars. Oh, this one they were a little nicer. Oh, I guess I would have been okay because I could have just looked up the moon in the book, and then Mars I was worried about, but I didn't read enough here because it says the mass of Mars is, let's see if it matches my information. So here's Mars. So I've got 6.42, and yeah, they listed as 6.418 times 10 to the 23rd, and then they give a radius and small difference in the last decimal place. All right, so I'll use the numbers from the problem here. And again, 6.67 times 10 to the negative 11 for the number, the mass. 6.418 times 10 to the 23rd kilograms, and 3.38 times 10 to the 6th meters. I didn't put units for other ones, so let me leave that off squared. And the units would be the same discussion we just had, so I'll kind of leave that one alone here. And then punch in my numbers. 6.67 times 10 to the negative 11. 6.418 times 10 to the 23rd. Divided by 3.38 times 10 to the 6th squared. And I get a number on Mars of about 3.74 meters per second. Still significantly less than the Earth. I'm not sure how much less. 2.6 times less. Okay, so 250%, 260% less. So pretty small, but about twice as big still as the moon. So there'd probably be less bouncing and jumping on Mars than on the moon. But still small enough that we could probably return a launch vehicle. And that was always the concern. And the fortunate part of the moon was you could put a lunar lander on it and actually push something back into orbit by having very little rocket fuel, or just an explosion of some dynamite would be enough to lift it off of the surface of the moon and put it back into the orbit. So the lunar lander had a little return capsule that was just, underneath it just had an explosion of dynamite here, or TNT, and lifted it off. Whereas this might take a little bit more. And getting then a rocket off of Earth would be a lot harder than Mars. But getting it to Mars and then getting it off of Mars is really a challenge. In fact, as a side note here, NASA has just started in a very interesting experiment. They're going to try to return some Mars sample, return it to Earth, and it's something like a 10-year mission. The first rocket goes out and just sends the lander, and I think that one's already landed. I think that's one of the mini rovers and Curiosity ones that actually landed. And that one's driving around on the surface taking test tubes, and then it's going to eventually run out of fuel and energy and just to leave a bag on the ground. Fortunately, no one's there to steal it. But meanwhile, they're going to send another rocket that its payload is nothing more than a small rocket, as much as they can get, that's going to land on the surface, find the bag, put the bag into its little pouch, and then launch. But it's only going to have enough fuel to get it into orbit. So it can get it off the surface, but it can't get it all the way away from Mars and back to Earth. So then there's a third rocket that NASA's going to send up. And that's why this is going to take a while. And that one's going to go all the way to Mars and rendezvous with the one in orbit, grab the bag from the satellite orbiting in Mars, grab it, and now it has enough fuel because it never needed to go down to Mars and leave Mars. It just had to go to orbit. Of course, we'd have to wait till Mars and the Earth, which go around, get all lined up again. But then it's going to leave the orbit of Mars and come back and land in the Earth. And so all of this is something like a 10-year mission. So long-term planning, crazy to think about, but it will be a big step forward in terms of science. It'll be the first time that we'll actually get a sample from Mars, at least a direct sample. Because this leads to another interesting piece of this small number, is asteroids colliding into Mars can send up debris with such a small acceleration that they actually leave Mars. And if they leave Mars, they might then go towards the sun, and the Earth comes by and traps it with its gravitational pull and sucks it in. So we actually have, believe it or not, a number of rock samples from Mars just because of the way things are situated. We've got the sun here. The third rock from the sun is the Earth. The fourth rock from the sun is Mars. And the asteroid belt is just beyond it. So the asteroids collide in with Mars, send up the debris, the sun pulls it in, the Earth gets close by and pulls that in. And so because of the asteroid belt, and because Mars is one planet out further, and because Mars is small enough to have a small acceleration, we actually find then these rocks on top of Antarctica. And when you find rocks on top of 9,000 feet of ice, the conclusion is they fell in from above. And so every summer, a group of scientists explore the ice looking for new pieces that have fallen in, and very, very likely that those are from Mars or asteroids themselves. So they've got to look at the composition of them a little bit and decide, are they asteroids themselves, or are they actually pieces from Mars? The other planets won't quite do that. All right, well, I babbled on about other things, but hopefully that was enlightening, especially you guys in the life science, because they're using those. In fact, right now, there is some evidence that maybe there was microbe life in some of these asteroids. And so they're constantly looking at them, and there are some indications that maybe they're finding some fossilized microbes, although they're something like 10 times smaller than the smallest known microbes on Earth. And so a lot of people have a lot of questions about, was that really life a long time ago? But anyways, hoping to find some good rocks, hoping to find some fossilized life. We have a lot of speculation that life once existed on Mars, maybe even still exists deep down, but we keep probing Mars. And, of course, the other big one is Io, the moon of Jupiter. But those in our solar system have the biggest promise of finding any life on Mars. Oh, Io's or Gamamine? Ooh, it might be Gamamine. But one of the moons of Jupiter, because of the tidal forces and the way things keep the ice from freezing. And so that's an interesting warming of the planet that isn't directly from the sun. Normally you would have thought, oh, no, it's too far from the sun, but there's some energy added to tidal forces as it orbits, and that keeps things warmer than expected. All right, well, better stop this problem. Hopefully this will help you with the problem and maybe entertain you a little bit into what do they call that? Astrobiology, what kind of life could possibly exist, and how might it be different than life on Earth. It's an interesting scientific field that some of you might be interested in. All right, bye now.